Well, we have talked about so far that there's in general no difference between pushing and pulling forces. In other words, they have the same effect regardless of whether you push or pull. And up until now, up until chapter 4 anyway, we were talking about point equilibrium at a pulley or at a knot or something like that, and where we saw that there was no difference in how you applied the force. However, in chapter 4, we have objects that have shape and size and weight often. And so in those cases, it does make a difference how and where you apply the force. All right, so let's look at this two-dimensional object here. It doesn't have any dimensions, but it does have some shape, as you can see. And let's put a point A here and apply a force down at that angle, at some angle theta. So there's a magnitude of force there. And I'm going to compare it to this scenario where I'm going to apply the same force at the same angle, but at a different location. So where is the maximum effect, or what is the difference in the effect between these two applications? You might say that, well, we'll call this scenario 1 and this one scenario 2. This one does have a longer lever arm. Does it make it a max? Does it make the moment about point A greater in this case? Or does scenario 2 have a higher effect or a greater effect? Well, just looking at the pictures without doing some further analysis, without knowing what those dimensions might be, it may be difficult to guess. So what let's do, let's use a principle that we've discussed. We call it the principle of transmissibility. And I can kind of do that here on this. Just draw a line of action of that force. And then I'm going to redraw that force over here on scenario 3 at this point right here, where that is going to be the line of action, or on the line of action that we have in scenario 1. Now, which one has the greatest effect? Here it's much easier to see. For example, if I were to find out the moment, well, first of all, let's just establish, because the line of action applies by the principle of transmissibility, 1 and 3 are the same. So 1 is equivalent to 3. But which is greater, 1 and 3 or 2? Which has the greatest effect about, or greatest moment about A? So let's use Varignon now to try to do some analysis. Let's say that there is a cosine component this way and a sine component this way. The sine component has no effect as far as moment about point A, because the sine component goes through point A. However, the cosine component has this lever arm, so I'll call this D2. If I look at scenario 3, I'll have the same cosine component and the same sine component. However, the sine component again has no effect because there is no lever arm. However, the cosine component has this lever arm. We'll call it D3. So now you can see that only the cosine component causes moment. It has a smaller lever arm here. The cosine component is the only thing that causes moment and has a much larger lever arm here. So in this case, scenario 2 has the greatest effect, has the greatest moment. So by that you can kind of guess that if I were to look at this, if we were to look at this object, which has the greater, or how can you reposition those forces, these two forces that are applied, for the greatest moment? It's pretty obvious perhaps, but if I were to, instead of applying them right there, let's say I applied the forces at a right angle and kept the magnitudes the same, those would have a greater effect or greater moment about point A. How about this one over here, this three-dimensional object? Let me zoom in a little bit on this. Is there a way to reposition or reapply that 20 Newton force to have a greater moment about z-axis? So this is a wrench. We're trying to unscrew some bolt here at point O. And can I reposition that 20 Newton force at a different angle, at a different place or something like that, to have a greater moment about Z, which we're trying to use to unscrew that bolt? Well, if you look carefully at this is already applied at a 90-degree angle. So I can't apply it at a different angle and have a greater moment. So this is the maximum moment now, as long as I'm applying it at that 200 Newton distance. If I were to apply it way out here and have a greater lever arm, then I might have a greater moment. But in this scenario, if I stick with applying it at this point A, then it is already the maximum moment. What we have here is a couple of scenarios here. A two-dimensional object, which we've already talked about, which this 500 Newton force applied at the end of this curved member. What I'd like you to do is think about how you can reposition that 500 Newton force so that it has a greater moment, maybe the maximum moment, about point O. How could you're going to still apply it at that point, but you're going to change the angle or change something about it so that it has a maximum moment. So anyway, what I want you to look for is how to find the maximum, and then conversely, what's the minimum moment? In other words, how do you draw that force so that it has the minimum moment? Then in this three-dimensional object, we have four scenarios I want you to consider. I'm going to apply a force right there, or I'm going to apply the force way out there and in the same kind of orientation, but just applied at the end of the pipe. I want you to compare those two, and then I want you to compare it to applying the force right there versus right there. So in other words, the force is going to be the same magnitude in all scenarios. See if you can find out the maximum moment about point O for each of those four scenarios. So go ahead and pause the video and work on that for a few minutes, and then we'll talk about the solution. Okay, how do we find out the maximum moment of that two-dimensional object? Well, it may be pretty easy to see, but this is the lever arm. If I apply the force at this point, how can I redraw that force so that it has the maximum lever arm, or the maximum moment? It would be so that it would be drawn so that the 500 Newton force is perpendicular to the lever arm. That's the way we always find the maximum moment, where that is the right angle. And then in the scenario over here, if I want to find the minimum, then I would draw the force so that it has zero lever arm by the principle of transmissibility. So if I were to extend this back to here, there wouldn't be any lever arm at all. So anyway, this will be the minimum, this will be the maximum. Now how about these two guys, that versus this? Well, again, by principle of transmissibility, it doesn't matter if I apply the force here or if I apply the force there. So in this case, the moment about point O, which is actually a moment about the x-axis. We're going to talk about the axes in a few minutes, but or in the next video, but the moment is going to be the same, the moment about point O, because there is no difference in whether I apply the force here or apply the force here because of transmissibility. Now in this case, excuse me, in case 2 versus case 3, I'm having a moment about point O around the x-axis here, and it'll have some magnitude based on that lever arm. In this case, because I'm applying it here, it's going to have the same magnitude because it has the same lever arm. It's going to be rotating about that axis a different way, but it has the same magnitude. So 2 versus 3 are going to be the same magnitude as well. 3 versus 4 does have a little bit of a difference. In other words, this one has a magnitude only about the y-axis. In this case, this is going to have something trying to rotate about the z-axis as well as rotating about the y-axis. So this one, because it has trying to rotate about two axes, then it actually is the greater moment. We can also do this with r cross f. You can say that this could be the r for that one, and this is going to be the R for that one, and clearly this one has a R4 has a greater length, if you will, than R3. So as we get a little more familiar about it, you'll come to understand better that this one has the greater effect.